All right, this is the video on forces and the introduction of forces. So just to start off, we need to distinguish something, the difference between speed and velocity. So it might not seem like a difference, but there is a difference, right? So speed is a measure of how fast you are going, but velocity is a measure of how fast you are going in a given direction. So speed is a scalar quantity and velocity is a vector quantity. So velocity is speed plus direction. Now, acceleration. Now, if you've ever heard the word acceleration, uh, like uh, you probably just say, well, that just means you're speeding up. But in physics, it has a very specific definition. Acceleration is how fast velocity changes. It is a vector quantity, and a net force must be applied in order for an object to accelerate. Now, there are three ways to accelerate. You can speed up, you can slow down, and you can turn. But could you accelerate without changing speed? So let's just look at the controls in a car. So what controls in a car change the speed? That's going to be the gas pedal and the brake pedal. That changes the speed of the car. You can speed up, you can slow down. Now, what controls in a car will always cause a change in velocity, but not necessarily a change in speed? That's going to be the steering wheel. Will change the velocity without necessarily changing the speed. Velocity is speed plus direction. So you could take a turn going the same speed, but you would be changing direction. So you would be changing your velocity. Now, what controls in a car can cause an acceleration? All of them. The gas pedal, the brake pedal, and the steering wheel will all cause an acceleration because they will either change the speed or change the direction of the car. So acceleration is not how much velocity changes, but it's how fast velocity changes. So it's a change in velocity over change in time. So the arrow above some of these variables represent a vector quantity. The Greek letter delta means change in. So if we look at this equation, you need to know the starting velocity, the ending velocity, and the time interval over which this change took place. Now, the unit for the acceleration is unit of velocity per unit time, meters per second squared. Now, meters per second squared isn't a unit, but what that means is it's meters per second per second. How much faster every second is that object getting? So if we did these practice problems, suppose a driver increases her velocity from 5 meters per second to 12 meters per second in a time interval of half a second. So I just plug it into that equation. So it's 12, which is that final velocity, minus the initial velocity, which is 5, divided by half a second. I get 14 meters per second squared. Now, this next problem is a driver decreases her velocity from 12 meters per second to 5 meters per second in a time interval of half a second. Well, all I do is I plug that in. Now, this time the final acceleration, or sorry, the final velocity is 5 meters per second, and the initial velocity, what she started at, is 12. So I'm going to have a negative. I'm going to have a negative of acceleration, negative 14 meters per second squared. Now, this last one, suppose a driver travels at a constant velocity of 12 meters per second in a time interval of half a second. So 0 meters per second squared. So because if you're traveling at a constant velocity, you are not accelerating. But what is negative acceleration? Now, negative acceleration does not necessarily mean an object is slowing down. If an object is speeding up, the acceleration will be in the same direction as the velocity. If an object is slowing down, the acceleration will be in the opposite direction as the velocity. And if an object is at rest or at a constant velocity, which remember are the same thing, the acceleration will be 0. So you can see here an object is speeding up, the acceleration is going to be the same direction as the velocity. Where here the object is slowing down, the velocity is going to be the acceleration is in the opposite direction of the velocity, and those are the other two options, but it is going in the negative direction. So when we talk about graphing them, when graphing an object's position versus time, the slope of that line is the velocity. When graphing an object's velocity versus time, the slope of that line is acceleration. So think about what slope is, rise over run. So delta y divided by delta x. So the acceleration is change in velocity, the rise, divided by the change in the time. That would be the slope. The acceleration is just the slope of the velocity graph. So like this just sort of all ties together about the special of relativity. In physics terms, there is no difference between being at rest and moving at a constant velocity, and acceleration is the only absolute or real motion. So let's ask this question: what forces are acting on you right now? So a force is a push or a pull in a given direction. So force is a vector quantity, which means it has both magnitude and direction. Now the unit for the force is the Newton, represented by capital N. Now, we represent a force by a line with an arrow to indicate the magnitude and direction of the force. So there are 6 different types of forces that we'll be learning about. So there's the force of gravity, the normal force, the perpendicular support force, an applied force, which is a force from a person or an object onto another person or object that attempts to change the motion in an object. Frictional force opposes sliding motion, drag, or air resistance. That's the fluid resistance that opposes motion through a fluid, and the force of tension from a rope, string, or spring. So now let's talk about net force. Forces can add to each other. Think about pushing a car. If one person is pushing in one direction and the other person is pushing in the opposite direction, those forces aren't going to help each other. But if they're pushing in the same direction, those forces will help each other. This is called net force and represented by sigma F. So net force is the sum of all forces acting on an object. So these are some examples that you can have. So you can see how those forces add together to be the net force. So you can see here that if you're pushing in the same direction, well, the net force, well, it's going to be larger. If you're pushing in opposite directions, they can balance each other out. And the last one is you can have, forces going at different angles, and you add them together. So this slide basically sums up like a lot of physics, a lot of like the Newtonian physics, balance versus unbalanced forces. So balanced forces, all forces cancel out. The net force is going to be 0 newtons. Net force is 0 newtons. The object is at rest or at a constant velocity in a straight line. Now, unbalanced forces, all the forces do not cancel out. The net force is not 0 newtons, and the object will be accelerating. So here's the example, right? If I just have an astronaut floating in space and I'm negating any like small gravitational forces, the net force acting on that astronaut is 0. Now, if that astronaut is moving at a constant velocity, like that in a straight line, the net force is also going to be 0 newtons, right? You add all of the forces together, they're going to balance out. Now, the reason why, like, this is where that theory of special relativity, and there is no difference between being at rest or at a constant velocity, because from these astronauts' perspective, neither one of them could say, I'm at rest, you're at a constant velocity, or I'm at a constant velocity, you're at rest, because they do not feel that motion. They cannot measure any motion because all that motion is going to be relative. But let's just say they get into a space shuttle, right? And I have an applied force, which means I do have a net force. It is accelerating. They strap themselves into that rocket, they are going to feel that. Now, the example that I like to use is that if you're driving in a car, if you're stopped at a stoplight, right, you do not feel that motion. You can drink a cup of water, you can throw something up and down. Everything like it seems normal to you. Now, if you're driving down the highway in a straight line at a constant speed, so constant velocity, like at 60, 70 miles per hour, you don't feel that motion. You can still drink a cup of water fine, you can toss something up in the air, you can take a nap, read a book, you will be fine. But if you're driving that fast and someone slams on that brake, you're going to feel that. You can feel the acceleration, but you can't feel being at rest or at a constant velocity. So that's why I put this up again. Physics terms, there is no difference between being at rest and moving at a constant velocity. Acceleration is the only real motion. And remember, there are 3 ways to accelerate: speed up, slow down, and turn. So let's just take a look at an example of kicking a football. So right here, somebody's holding the football ready to be kicked. Let's see what forces are acting on it, right? So what forces are acting on it are going to be gravity and the normal force. And you can make, I think, a small applied force, because this person is touching that football. The object is going to be at rest. It's just sitting there. The net force is going to be 0. All the forces balance out, so the forces are balanced. So you can see here I've got gravity, I've got a normal force, I've got an applied force, and the net force is 0, right? It's at rest. Now let's take a look at the next scenario. So the kicker winds up and kicks the football. So now I do have gravity working on it. I don't have a normal force. I don't have that perpendicular support force. I have an applied force. That might be it. You can make a case for drag or air resistance, but I don't think I put that on here. The object is going to be accelerating because it's speeding up. The net force is going to be not 0, and the forces are unbalanced. So if I look at this, I've got a gravitational force, I've got a strong applied force. This is going to be my net force. It is accelerating. Now, as a football is traveling through the air, I do have probably some drag acting on it, and I do have gravity. I don't have an applied force anymore. I don't have the normal force. So gravity and drag. Now the object is accelerating. Now, even though he's not kicking it, think about the path that the football takes. It's going to go up and come back down. It goes in a parabolic curve. It is turning. It is accelerating. So that means there will be a net force. And the forces are unbalanced. Now, these are the forces that are acting on it. So I've got gravity and I've got a small drag force, right? This is the net force. That is the direction that it is accelerating. So let's take a look at the deadlift, right? As the barbell is at rest on the ground, the net force is going to be 0. It's at rest. The forces are balanced. Now, as it's lifting off the ground at a constant velocity, the net force is still going to be 0 because the gravitational force balances out that pulling force. But you do have to get it to accelerating just briefly off the ground. But once it's moving, you can pull it at a constant velocity. The forces are going to be balanced. Now, as that person drops the barbell, lets it go, it's going to be accelerating. So the net force is not going to be 0, and the forces are unbalanced. So how can we represent forces? And we represent forces with a free body diagram, or FBD. So to make a free body diagram, you take the following steps. You draw a dot at the center of the mass, draw arrows pointing away from the dot representing the forces. The arrows should be scaled and label those forces. So let's get some practice, like a dog pushing a wheelchair at a constant velocity. So we know that we have gravity, we're going to have a normal force, we have an applied force, and there is going to be a small frictional force. That's what's resisting, like in the axles of the wheels. So the free body diagram, like see, I've got gravity, I've got a normal force, I've got applied force, and I've got that frictional force. The net force is going to be 0 newtons, right? Because remember, it's balanced because it's at a constant velocity. That's what the free body diagram will look like. Now, a horse skidding to a stop. Well, the forces, let's see here, I've got gravity, I've got the normal force, I've got friction, that's what's slowing it down. The free body diagram, it's going to look like this. So I've got gravity, I've got normal force. Now I've got a frictional force that's slowing it down. Now notice the horse is sliding to the right, but that frictional force is providing a force to the left to slow it down. This would be the free body diagram. I have a net force acting in the opposite direction that it's moving because it's slowing down. It's actually accelerating in the opposite direction of that velocity. A skydiver at terminal velocity. So that means he's traveling at a constant velocity on the way down. So I've got gravity and I've got the drag forces. Now at terminal velocity, the gravitational force balances out that drag force. So the net force is going to be 0 newtons. And this is what that free body diagram will look like. Earth orbiting the sun. So basically, the only force I have acting in this one is going to be gravity, right? I've got gravity acting on it going down, and the net force is going towards the sun, right? That is going to be the free body diagram for Earth going around the sun. Bowling ball. So I've got gravity and I've got a normal force as it's rolling. So I've got gravity and normal force. The net force is 0. It's traveling at a constant velocity in a straight line. So now you can also make like a hook shot for bowling, right? So in this example, I have got gravity and I've got normal force, but also I have a frictional force as it's rolling. It's going to be pushing or accelerating that ball towards the pins. I have a net force like this. This is what it's going to look like. In this one, a girl like throws something and the dog pulls on her on the leash. So I use this example because I have a tension force, because I've got gravity, normal force, a large tension force, and probably a frictional force as she tries to stay upright. And the net force, she is accelerating in that direction. So there are a couple activities that you can do to help yourself out. Name that motion. This is all on Physics Classroom. Balance versus unbalanced force, and match that free body diagram. These are all great activities that will help you out understand these and get practice with identifying forces, net forces, free body diagrams. So now we did talk about the force of gravity a little bit, but we do need to distinguish the difference between mass and weight. So mass is the measure of the amount of matter or stuff in an object. It is measured in kilograms, or kg. It does not depend on location. It is closely related to inertia. It cannot be measured directly. So it only has a magnitude, which makes it a scalar quantity. Now, weight is the measure of the force of gravity on an object. It is measured in newtons, represented by a capital N, and it does change with location. It is closely related to gravity, and it can be measured directly with a scale. It has both a direction and a magnitude, which makes it a vector quantity. So you can see that diagram off to the right. You've got a 2 kilogram mass. It's always going to have 2 kilograms. It's not dependent on location. No matter where it is, it always has that amount of stuff. But you can see if it goes on to different planets or if it's in deep space, that does change the gravitational force acting on it. So weight, what does it mean that weight is closely related to gravity and can change due to location? So gravity, if you were to go to the moon or another planet, your weight would also change. So you can see that there's a link here that will show your weight on different planets. You can see this astronaut has a mass of 100 kilograms on Earth and has a weight of 980 newtons. But on the moon, the mass is still 100 kilograms. It still does not change the amount of stuff they're made out of, but the weight would be 162.2 newtons. So you can see here there are some scales at some museums that will tell you your weight on the moon. Now, gravity also changes depending on your latitude and altitude. Gravity changes based on where you are on Earth. So there's less gravity the farther away from the center of the Earth. Technically, walking up to the second level of floor lessened that gravitational pull on you. You lost weight by walking up the stairs. The Earth also bulges towards the equator, meaning it is farther away from the center, meaning gravity is weaker. There's also something else that'll affect it, like think about an elevator. You do feel weird on an elevator. You feel a little lighter when the elevator is accelerating down because the floor is moving out beneath you. So the Earth is rotating. At the equator, is moving a lot faster than at the poles. At the equator, the ground is falling out from beneath you a little bit more than anywhere else on Earth, just like an elevator. If it only took Earth 90 minutes to make a full rotation, anyone standing on the equator would appear to be weightless. Notice I said appear, which brings us to our next topic. So you can see here the scale on different, you're going to weigh differently because of the way the Earth is rotating, but also it bulges at the center. So you can see it does depend on place. Now, if we look at a scale, if someone were to step on a scale, that scale does not read the gravitational pull of the object. Gravity will pull that object down, pressing on the scale. The spring in the scale will push back with that perpendicular normal force. The reading on a scale shows a normal force, not the gravitational pull. In fact, how heavy you feel depends on that normal force. So if you've ever been on a roller coaster, you're going to feel lighter at some points and heavier at some points. But being on a roller coaster does not affect the gravitational pull that Earth is pulling on you. Uh, but it does change that normal force, how hard you're getting pressed down into that seat, which brings us to that next topic. Oh, there we go. So it's the normal gravitational force, which brings us to our next topic, actual weight versus apparent weight. So there is a difference between the gravitational pull on you and how heavy you feel. There are two different weights we need to talk about. Actual weight is the measure of the force of gravity on an object. It's just the force of gravity. Now, apparent weight is how heavy a person feels and is dependent on the normal force. So how does being in water affect a person's weight? So being in water does not affect the gravitational pull on the person. Uh, there's not a normal force acting on that person. Being in water does not affect the force of gravity on a person, but that buoyancy force, it is another force, is holding the person up, not the normal force. Now, this is not a normal force acting on the person. So in water, people feel weightless because that force is sort of spread out over their whole body and not just like at their feet. So they don't really feel you don't really feel your weight inside of water. That's why whales can be inside of water, but not, on land, right? It doesn't change the gravitational pull on things, right? So I've got that buoyant force. So weight and acceleration. In order to calculate the weight of an object, two things need to be known. The mass of an object, the acceleration of all objects on that planetary body. Now, why do we need to know the acceleration? Let me ask you a question. If I put a bowling ball and feathers, what will hit the ground first, right? They would both hit the ground at the same time in a vacuum. So the objects accelerate. You can see your Earth, it says 9.81 meters per second squared down. We use 10 in this class, but you can see it's different on different planets. So the acceleration on Earth is actually negative 9.807 meters per second squared. That's just an average, right? The acceleration of objects falling depends on your latitude and altitude and can range from negative 9.764 to negative 9.834 meters per second on Earth. Now, when I drop something in this room, the acceleration in this room is actually negative 9.79929 meters per second squared. So you can use that link to find the acceleration all over the planet Earth. But we're just going to simplify the math by using negative 10 meters per second squared, right? So we're just going to say, yep, on planet Earth, the acceleration of all objects falling on Earth is negative 10 meters per second squared. So here's how you calculate weight. The force of gravity will be negative, as it is always pointing down to the center of the Earth. Now, when we ask someone how much something weighs, no one says a negative number. We only say the magnitude. But recognize that when we are doing problems in this class, the force of gravity will be negative because it is pointing down. Remember that the acceleration due to gravity is negative 10 meters per second squared. Some places you may see the variable acceleration gravity written as just a lowercase g and is 10 meters per second squared. This only gets the magnitude, but it is still pointing down. So if we did a couple practice problems, an object has a mass of 12 kilograms. What is the weight of that object on Earth? So I'm looking for the weight, the force of gravity, looking for the mass. All I do is I multiply those together and I get 120 newtons down. An object has a weight of 90 newtons. What is the mass of the object? So I'm looking for the mass, and I know the gravity. Then I just divide that and I get 9 kilograms, right? So you're never going to get a negative number for the mass. An object is on Mars and has a mass of 50 kilograms and weighs negative 186 newtons. What is the acceleration of all objects on that planet? Well, if I just plug everything into it, I get the acceleration is negative 3.72 meters per second squared. So if you're on Mars, yes, you're going to have objects fall at a different rate. So how are we able to push a car even though it is so heavy? So let's just look at an example, right? So we know that we're going to draw a free body diagram. I've got the force of gravity. I've got the normal force. I've got an applied force, and I've got a small frictional force. So I do have a net force if it's accelerating, if you're pushing a car. But you are able to push a car, even though it is really heavy. Now think about it this way. You're not pushing against the weight because the weight is pulled down. What's resisting that pushing motion is going to be the mass. The mass is resisting that motion, and we said it is tied closely. We said that it's tied closely to inertia, and in 2018, the Tesla Roadster was launched into space and has been traveling at a constant velocity, 75,000 miles per hour. Now, in physics terms, there is no difference between something at rest and something traveling at a constant velocity. Accelerating both the car in space and the car on the ground with the parking brake off at the same rate would take the same net force, right? So when you're pushing a car, you're not actually pushing against the weight. You're pushing against the inertia. The inertia is resisting that pushing motion. It's resisting that change. Now, lifting a car is a different story altogether. So the last thing is this is a little activity where you can find your weight on other planets. So you're just finding that your weight on other planets, 50 kilogram person, and this would be what it is, right? So you're calculating what the acceleration of all the objects would be. Now the acceleration is going to be down because it's falling in a downward direction. So here are some questions. What is mass? We already went over these. What is the unit for mass? Does mass depend on location? Can mass be measured directly? Is mass a scalar quantity or a vector? Explain your answer. And what is weight? What is the unit for weight? Does weight depend on location? Can weight be measured directly? Is weight a scalar quantity or a vector quantity? Explain your answer. And Why does the weight of an object or person change on other planets, but the mass remains the same? How do mass and weight relate to each other? So it has to do with that equation. All right, so this just finishes up the video on forces, mass, and weight. Just as a final thought, remember there's too much unknown in the universe to take a break from learning. Get out there and question everything.